in a previous section in the 3D graph, looked kind of like a bowl opening down. We looked at contours by slicing the 3D horizontally and dropping the pictures to the floor. A cross-sectional model is a vertical slice. So the lesson will show you in lovely colors how it looks if you slice it downward. But what we want to do is see what happens if you don't happen to have the big picture, what kind of function you'll get if you have the original function. Now, to do a slice, one of the variables, either x or y, has to be constant. So for this cross-sectional model, I'm going to let y be a constant. The function is the profit to produce and sell x tables and y chairs. So I'm going to assume that I'm always going to make 10 chairs. And we'll see what happens as the tables vary. So the function will look like p of x 10. And I just go through and every place there's a y, I put a 10. So I have 200x plus 140 times 10 minus 12x squared minus 4 times 10 squared, which is 100, plus 2x times 10 minus 700. Putting all this together, 200x, let's do the variable part first, minus 12x squared plus 20x, and then I've got 1,400 here, minus 400 gives me 1,000, minus 700 gives me plus 300. So I have this function, let's write it like we would like to, highest exponent first, negative 12x squared plus 220x plus 300. What I have here now is a function of one variable. You should recognize it, negative 12x squared, it's a parabola. Because of this negative leading coefficient, it opens down. So it would look something like that. So you have one variable, and this is what your slice will look like. You can always figure this out by putting in a constant, but that's just one constant. And we have a function. So we know what one slice is. The number of chairs is 10, constant, but x is the number of tables, and I can see what my profit will be as I vary the number of chairs and tables. I could say, what do I get if I put in x equal to 3, or if I put in x equal to 5? So we'll look at that a little bit when we go look at the table of values that can go with this function. So let's look at that now. This table is part of one you've seen before of our multivariable function profit from selling x tables and y chairs. Remember that the x values go across the top row, the y values go down the first column, and the values in here are the actual function values. That is the profit. If I want to know the profit for selling 5 tables and 10 chairs, that would be $1,100 to produce and sell those. What we want to look at now, though, is how you can look at the table and come up with your own model that's a cross-sectional model holding one of the variables constant. So since I looked before at y equal to 10 tables, 10 chairs, and held that constant, we'll do that again. My x's will change. The number of tables will change, and so I will keep that row for my input variable values. The y values I want to maintain at 10, so this row will be the y values that I will graph as my function values, not the y values, excuse me, the profit values I will graph as the function values. We saw last time that when I have y as a constant, I got a quadratic function, negative x squared plus 220x plus 300. Let's see if we can get that from the data and use Excel in a trend line. If I set this up to graph in Excel, I'll put it in two columns. I'll have my x values down the first column, 0, 5, 10. I'll have my y value, keep saying y. Hard habit to break. My profit values down the second column, 300, 1100, and 1300. Now 3 points is really not enough to graph a parabola. You really need a little bit more, maybe 1 or 2 more points. So I'm going to pretend I've got some more data that I'm going to use. When you graph, you highlight the data. And when you highlight the data, that means the x and the p as well. Okay? We want the inputs here and the outputs there. The second thing you do is select the chart tab. And that way you'll come up with a whole group of chart selections. And then you select scatter. We only ever use a scatter graph in Math 1526 because it's a horizontal axis and a vertical axis that depends on the horizontal values. The scatter that we want to use is one that's just dots. So we'll highlight, click on charts, find the scatter graph, which sometimes is visible if your screen is wide and sometimes not. And so what we come up with when we do that graph, at 0, for x, p is about 300. At 5, for x, we've got 1100. I'm going to pretend like that's 1100. Okay. At 10, I have 1300, which is higher, a little bit higher than that. And I didn't do the next value, but it drops a little bit. So it's, I think, about 900. So if we went a little bit further, the graph would go up and drop. And I'm not saying this is the highest value, but for the data that we have, this is all we see. One more value there. And in Excel, if we want to actually get our trend line, the next thing to do is click on a dot. And if I click on a dot, they all highlight. And we can do a trend line. So remember your steps for a trend line. First thing you do is click on a point. And when you click on that point, it should highlight all of them. And then in the Excel menu, which is at the very top of the screen, you will now have a chart word, and you scroll down and it says add trend line. So the box opens. So when the box opens, we go, well, we know this is quadratic. It's a parabola, it's quadratic, it opens down. But that's not what you'll see. What you'll see in the box is polynomial of order 2. It'll say polynomial, and you'll have to select your order because it was a squared function, and that's what a quadratic is x squared. So you have to remember all that. And then after you select that, you look for the options word, and in there, in that part of the box, it'll say display equation on chart. And so this is what you will do to get the equation that we got before. The equation that we got before, let me get rid of my data table. I don't want to get rid of all of it. We got before P of x10 is negative 12x squared plus 220x plus 700. That's the value that we got for P equal to 10. So what do we do with that? Well, our data table, my x values were 0, 5, 10. Suppose I want to know what happens when x is 3. What happens if I'm only going to sell 3 tables? My x values can change, right? But let's say I want to find P of 310. Well, now I can do that. If I want to know if x is 3, I'm selling 3 tables, what's my profit going to be? I plug in x equal to 3 in here. I come up with 852. That's in here somewhere. And so I found out that actually it's 852. And remember, this is from an actual function. Now, if I did not have that function to begin with, the one I had up earlier, this is the only way I could estimate that. I mean, you could estimate, but a lot of things that you do may not work. You may think it's linear, and that doesn't work. So that this is a way that we can predict values. This is called interpolate because it's inside. Now we're going to move into the beginning of calculus with multivariable functions. And the first part of this is to understand the partial derivatives. Partial derivatives, not just a derivative. If you've forgotten, the definition of derivative, instantaneous rate of change of the output value, which is the function value, as the input value, the variable value, changes. So it's a rate of change. You've done a lot of derivatives with functions of a single variable, f of x. We could write that derivative as f prime of x. We won't be using primes for the most part here because we don't have a derivative. This means the derivative of f with respect to x. But we have another notation that says the derivative of f with respect to x. We use this a lot, and it tells us the function is x and the function is f and the variable is x. There's another notation we don't use as often, the derivative of f with respect to x, where x is a subscript. And we do use something similar to this. So these two notations are moving into the partial derivative. Now, why is it partial? Well, now we're looking at multivariable functions, and let's look at one that has 3 variables. F has x and y and z, so maybe there are x tables and y chairs and z desks. So maybe we have several items in our inventory. Now, if I want to take a partial derivative of this function, I have 3 variables. I have 3 partial derivatives. So the notation that's similar to df dx is this funny little thing I can't do well. It's a partial symbol. It's sort of like a squirrely d. Derivative of f with respect to x. That's 1. Partial derivative of f with respect to y. Partial derivative of f with respect to z. So I have 3 variables, 3 partial derivatives. If I have 4 variables or 2 variables, I have the same number of partial derivatives as I do variables. Well, let's look at a multivariable function that we looked at previously, our profit function, p of xy, where x was the number of tables and y was the number of chairs. The function is 200x plus 140y minus 12x squared minus 4y squared plus 2xy minus 700. So this is my function of 2 variables. We previously looked at the function when we held y constant at 10 chairs. When we did that, letting y equal 10 in each space, we ended up with the function negative 12x squared plus 220x plus 300. Function of a single variable because we were holding the number of chairs y constant at 10. I'm going to call this a new name. I'm going to call it g of x, a function of a single variable. You know how to take derivatives of functions of one variable. You did know how. We're going to review that. G prime of x, but since we're not going to be using primes in multivariable, let's call that the derivative of g with respect to x. Negative 12 is a constant multiplier. Derivative of x squared, 2 comes around front, times x, now to the first, plus 220 is a constant multiplier. Derivative of x is 1, plus derivative of 300 is 0. Constants all by themselves, the derivative is 0. So this is g prime of x. But g of x was a function based on a multivariable function. So I can actually call this g prime of x the partial of p with respect to x. It is negative 24x plus 220. I could also call that the partial of p with respect to x using the subscript notation. I could write it either way. Well, suppose, since I have my partial derivative now, I want to find out what happens if I have a value for x. So I could find the partial of p with respect to x at x equal to 3. And I know that y is equal to 10. I have to have those together. Negative 24 times 3 plus 220. And I can also write that the partial of p with respect to x at the point 310. And down here, instead of this notation, I could also just put the point down there, 310. There are various notations you'll see. Plug that in, and I have found out that the value that I get is 148. That is the way profit changes when I'm producing and selling 3 tables and 10 chairs. And so that's the amount to produce and sell one more table, because x varies. The 10 will stay constant. If I wanted to find the value when I have 10 chairs and 8 tables, I just plug 8 in here and I have a different value. So when you have a function like this, the wording is important as far as what the meaning is. Remember that a rate of change is for one more item. This is actually also marginal profit because it is a change in profit with respect to an item or a quantity that is produced and sold. So I do have marginal profit. And I can say this means, by 148, when 3 tables and 10 chairs are produced and sold, profit increases $148. And there are a couple ways I can say it after that. I could just say per table. So that means every time there's one more table. Or I could say for each additional table produced and sold. So you can either say for each additional table produced and sold, which gets the marginal profit idea, or you could say per table. And it means exactly the same thing. But that's what a partial derivative does. It is a rate of change in the function as an input changes its value. In this section, we finally get to actually find some partial derivatives. So we have a function, f of xy, equals x squared plus y squared. In order to find a partial derivative, there's only one variable. So if I want to find the partial of f with respect to x is the variable. X changes. Y is a constant. This is like saying x squared plus 4 squared. The y is a constant. So if I take the derivative of the x part, using the power rule, I get 2x plus. With the derivative of y, there's no x attached to it at all. It's like the derivative of 16. The derivative of 16 is 0. The derivative of y squared is 0. So the partial of f with respect to x is 2x. If I want to find the partial of f with respect to y, the y is the variable. Y will change. So that would be like saying 3 squared plus y squared. Well, the derivative of 3 squared is 0. The derivative of x squared then is 0, plus the derivative of the y part is 2y. So you hold one variable constant as you take the derivative with respect to the other variable. So let's look at one a little more complicated. Suppose my function is f of rt equal to r to the 5th divided by t to the 3rd. And I want to start off, let's take the partial of f with respect to r. Okay, if r is the variable, the t to the 3rd in the bottom is a constant. I don't have to do quotient rule because I only have the variable r in one spot. So I keep the t cubed as is. I could think of this as moving the t cubed in front as a constant multiplier times r to the 5th. So if I do that, I keep the 1 over t cubed. The derivative of r to the 5th, 5 comes around front, times r, subtract 1, I get 4. So my derivative would be 5 r to the 4th over t to the 3rd. That would be the partial of f with respect to r. Well, suppose I want the partial of f with respect to t. There's a little bit of an issue here because t is in the bottom. So if I'm thinking about partial of f with respect to t, the r to the 5th is the constant multiplier in front, and I have 1 over t to the 3rd, which would be actually t to the negative 3. T is the variable I'm interested in now. So I keep my r to the 5th as a constant multiplier and take the derivative of t to the negative 3rd. So that would be negative 3t. When I subtract 1, I get negative 4 as the exponent. So I have negative 3 and r to the 5th in the numerator. And this t to the negative 4 I'll write in the denominator as t to the 4th. Typically, we don't leave negative exponents in answers. So to take the derivative of something in the denominator, if it's one little term like this, you don't have to use quotient rule. You will for other problems. You will have to do quotient rule. But for this one term like that, you just pull the denominator up with a negative exponent and take the derivative. F of PQ is equal to ln of P times Q plus 4P times e to the 2Q. I have two partial derivatives. I think I'll use the subscript notation this time. Partial of f with respect to p. Derivative of a logarithm. If the function is natural log, it's 1 over what's inside. There are links for derivatives and reminders from 1525 all throughout the lessons and on the web pages. So, derivative of a natural log is 1 over whatever's inside. However, I have the variable p, and q is a constant. So the derivative of pq is like the derivative of p times 3. The derivative of p times 3, the derivative of p is 1. Derivative of 3 is a constant multiplier. Derivative of p is 1. Q is a constant multiplier. If I have 3p, the derivative is 3. If I have qp, the derivative is q. Plus. Now here, p is the variable. Everything else that's in there is a constant. Everything else. So I have the 4, derivative of p is 1, and I have the e to the 2q. It's all constant. Now here I have a q and a q. They cancel, so I have 1 over p plus 4e to the 2q. So this is the partial derivative of f with respect to p. So p is the variable. Its derivative in both places, since it was just p, was 1. Partial of f with respect to q. Well, the natural log is still the same idea. So I have to do the derivative of the log of pq is 1 over pq, and then I multiply by the derivative of pq. Well, this looks a little bit more normal. The derivative of 3q would be 3, because the derivative of q is 1. So I keep my multiplier p, the derivative of q is 1, and so the derivative of pq is p, like the derivative of 3q is 3. Plus, now back up here, I have 4 times p. P is not the variable, q is the variable. It's really important that you write what you're doing, because you refer back to it. Q is the variable, so 4p up here is a constant multiplier. The derivative of e to the q. The derivative of an exponential function is the same thing, but because it's not just e to the q, you have to use the chain rule and multiply by derivative of the exponent, which gives you a 2. So here, this time my p's cancel. I have 1 over q plus, here's 4p, and there's a 2 down there. They're all the same level. 4 times 2 is 8p times e to the 2q. So these are the partial derivatives, both of them, that go with this function. F of x, y, z, function of 3 variables, equals x squared, y cubed, plus x, z squared, minus 4xyz. I have 3 variables. I have 3 partial derivatives. So, derivative with respect to x. X is the variable. The derivative of x squared is 2x. Y cubed is a constant multiplier. So I could write 2x and then keep my constant multiplier y cubed. Here's an x. The derivative of x is 1. Z squared is just multiplied by it. It's a constant multiplier. So I have 1 times z squared. Derivative with respect to x means the 4 and the y and the z are constant. So I have 4, derivative of x is 1, and y, z are constant multipliers. 2xy cubed plus z squared minus 4yz. See what the partial of f with respect to y looks like. Up here I have x squared times y cubed. Y is the variable, the x squared is a constant. Derivative of y cubed is 3y squared. Plus xz squared. No y. There's nothing it can be multiplied by. This is like 33. Derivative of a constant is 0. When there's no y attached, the whole term is constant. So the derivative is 0. Minus 4x is a constant. Derivative of y is 1, and z is a constant. So I have 3x squared y squared minus 4xz. Partial of x of f with respect to z. No z in the first term. That makes it a 0, remember? The second term, I have a multiplier of x. My variable is z. Derivative of z squared is 2z. Minus. Variable is z. I have 4xy as constant multipliers. Derivative of z is 1. So this partial is 2xz minus 4xy. Okay, 3 partial derivatives to go with 3 variables. And watch out for those that don't have a variable attached that give you a 0 derivative. F of xy equals x squared times 3x plus 2y to the 10th. So my parenthesis is raised to the 10th power. And I think I'll just look at one partial derivative this time. Let's just look at the partial of f with respect to x. Now, there are two x's. What's inside here can't be changed because it's to the 10th power, so that parenthesis is a unit. But since there are two x's, that means product rule. So, to take the derivative, you have to do the product rule. Product rule says, if I have two functions multiplied together and I want to take the derivative, first times derivative of the second plus second times derivative of the first, or however you memorized it. Okay, x is the variable, but we still have to do product rule. So I put down the first, which is x squared. Now, I'm multiplying times the derivative of the second. There's an x in here. I have to use power rule and chain rule. So the 10 comes around front. 3x plus 2y now to the 9th times the derivative of what's inside. Variable is x. The derivative of 3x is 3. 2y has no x attached. It's a constant. Derivative is 0. Plus second times derivative of the first. So it's 3x plus 2y to the 10th times the derivative of x squared, which is 2x. Now that is very messy. But I'm actually not going to simplify. I'm going to make it easy on us. Let's find out what the rate of change with respect to x is at the point when x is 1 and y is 0. Equals 1 times 10 times 3 times 1 plus 2 times 0 to the 9th. Ooh, 3 to the 9th. I don't think I did that. Plus 3 plus 0 to the 10th times 2 times 1. That really makes it messy. I really didn't want to do 3 to the 9th and 3 to the 10th. Tell you what I'm going to do. Let's see, I didn't close my parentheses here, did I? I left something out. Times 3. Oops. That. There. Okay. I think I'm going to backtrack a little bit here. I don't want to do both of those. Well, I guess I could. I don't have any idea what it's going to equal. 3 to the 9th times 3. Okay, that can multiply by the 10 here. Plus 3 to the 10th times 2. Okay, which is whatever that's equal to. You have to be really careful with these that you put 1 in for x and 0 in for y. So I've got 1 for x, 0 for y. That's a constant. 1 for x, 0 for y, 1 for x. Okay. So whatever that's equal to is the partial of f with respect to x. Actually, the partial of f with respect to y is much neater because if you do the quotient rule, excuse me, that's another problem. Product rule. First times derivative of the second with respect to y. Second times derivative of the first, derivative of the first will go to 0 because with respect to y, the derivative of an x term is 0. So the partial with respect to y is not nearly as bad. So this is our doozy of a problem. Now we're going to look at an application of partial derivatives. We're given a function that gives the weekly cost to manufacture X sports cars and Y vans. So C of XY is 100,000 plus 6,000X plus 4,000Y minus 50,000 times E raised to this power negative 0.01X minus 0.01Y. And the question is, find the marginal cost of a sports car at x equal to 100 and y equal to 150. Marginal cost. So you have to Try to remember what the marginals mean. A marginal in economics would be the change in the amount to produce one more of that particular item. In math, marginal, a change is a rate of change, which is a derivative. So we have to find the partial derivative of the cost function with respect to a sports car. So the partial with respect to x would be also written as c sub x. Okay? So we want to find the partial derivative with respect to x. And then after we do the partial derivative, the numbers go in. We do it in the order of the wording. Find the marginal cost, derivative of cost. Sports car tells us it's with respect to x at a point. So the last thing you do is put the numbers in. So a partial with respect to x of this function. 100,000 is a constant, derivative is 0. Plus 6,000 is a constant multiplier. The derivative of x is 1, so we just have 6,000. Plus 4,000y, there's no x here, so this is a constant just like the 100,000 was. I'll go ahead and put in my 0 so you remember to check for that part. Minus 50,000 is a constant multiplier. And now I need the derivative of the exponential function. The derivative of any exponential, you do have the exponential in the answer, e to the negative 0.01x minus 0.01y. But because of the chain rule, since it's not just one variable, I have to take the derivative of the exponent. Now remember, this is with respect to x. So the variable I have to take the derivative with respect to is the x. The derivative of x here would be negative 0.01, and this whole second part is another just y. There's no x in there, so it goes to 0 like our previous term with just a y did. So all of this is the derivative of the cost with respect to x. So let me simplify that a little bit. I have 6,000 minus, and another minus that I'm multiplying makes that a plus. 0.01 times this knocks that off 2 decimals, gives me 500e to the negative 0.01x minus 0.01y. So that's my partial derivative. What I have to do now is find the value of that at the point when x is 100 and y is 150, and then figure out what it really means. If I plug in 100 and 150, that gives me the exponent up here, 6,000 plus 500e to the negative 0.01 times 100 minus 0.01 times 150. You work all of those out, e to that power, multiply by 500, and then after you've done the e multiplied by 500, then you add the 6,000. That's a separate term. And this turns out to be about $6,041.04. So what does that really mean? It said find the marginal cost of the sports car, but what does it actually mean as far as what we're talking about here with two variables? Remember, we have two variables. So we can say when 150 vans are manufactured, remember, y is a constant, so I'm keeping 150 vans. When 150 vans are manufactured and 100 sports cars, cost will increase $6,041.04 for each additional sports car. Now this goes along with the marginal. It's a rate of change. Cost will increase. It will change when you manufacture one more sports car and then another sports car, as long as you stay pretty close to the 100. So The 101st sports car will cost the manufacturer $6,041.04 more than the 100 cars that it produced. And there's other wording that you can use for this, so be sure to check the varieties of wordings in the lesson examples to see other ways you might want to phrase that. Now, if you decide you want to find the marginal cost with respect to the number of vans, you would do the partial with respect to y, plug in both x and y numbers like we did, but the partial will be slightly different. And you'll have a different amount for producing one additional van while holding your sports cars constant at 100. Now we're going to look at a topic that we also saw back in single variable calculus, our higher order derivatives. But since we have partial derivatives now, one for each variable, we have numerous higher order derivatives even for one derivative. So if I take here, let's say that we're going to find the partial of f with respect to yxz. So if I see something like this, the first letter that I see after the f is a y. So the first thing I have to do is find the partial with respect to y. So the partial with respect to y means both x and z are treated as constants. So I see an x squared here. That means x squared is a constant multiplier. So it just sits down there. I'm multiplying by y cubed. I take the derivative with respect to y. Gives me 3y squared. In the next part, I have xz cubed. Well, there's no y. Since the derivative is with respect to y, the x and the z both are zeros when I take the derivative. Minus. Keep in mind, the y is the variable we're working with. So I have a y right here, so that 4x is a constant multiplier. The derivative of y is 1, and z is just another constant multiplier. So if I simplify this, I like to have my constants first. 3x squared y squared minus 4xz. That's my derivative with respect to y. Now, the second variable in my question is x. I have the partial with respect to y. I could take the partial with respect to y again, but it asked me to find the partial with respect to y and then x. So using the partial of f with respect to y, I now take the derivative of that with respect to x. So here's my x. That means the 3 is a constant multiplier, and so is the y squared. So the derivative of x squared is 2x, and I keep the y squared constant. Now, sometimes I tend to write all of the pieces that are constants first, and then take the derivative of the variable part. It doesn't matter. Most students seem to do it this way. But let's see, if I get to the next part, x is the variable. That means both the 4 and the z are constant multiples. So derivative of x is 1. And I now have 6xy squared minus 4z. The last variable they gave me was z, following y and x. So I take the partial with respect to y with respect to x. Now I'm going to take the partial derivative of this piece with respect to z. Z is the variable. There is not one z in this term. That derivative is 0. Minus the derivative of 4z, since z is the variable, would be 4. So that derivative, my third derivative with respect to each variable separately, is a negative 4. There are many possibilities. This asks for f with respect to y, then x, then z. For the functions we use, it shouldn't matter if you use each of those singly. You should end up with the same answer. I could find f sub x, y and not do z at all. There are any number of combinations that I could find for my derivative. You just always work the first variable derivative first, and from that derivative do the next one, and so on. I could do z at the end and have a fourth partial derivative. There's just many possibilities with these. Let's look at this function now in terms of p and q. ln of the quantity pq minus 4 times p times e raised to the power q squared. And I want to find the partial of f with respect to p, then p again, and then q. So let's look at the partial of f with respect to p. And you have to think, what was that derivative of a logarithm? Well, the derivative of ln x is 1 over x. ln u, the derivative would be 1 over u times the derivative of u. So we don't just have a p, we have a quantity. So we think of the chain rule with the derivative of a log is 1 over whatever's inside, pq, multiplied by the derivative of what's inside. Now the derivative of pq with respect to p, the derivative of p is 1 and the q is a constant multiplier that just stays with it. So this would be the derivative of the first term minus the derivative with respect to p. 4 is a constant. The derivative of p is 1 and the e to the q squared is a constant multiplier. Let's simplify this a little bit and note that there's a q here and a q here that we can cancel. So I have 1 over p minus 4e to the q squared. That's the partial of f with respect to p. If I find the partial of f with respect to p a second time, I'll only use this term because there's not a p left in that one. And I can't just take the derivative of p as it sits here. We have to rewrite this expression as p to the negative 1 in order to take the derivative of it. Use the power rule. The negative comes around front times p, and I subtract 1, makes that negative 2. And then, as I said before, there's no p here, so the derivative is 0. So this derivative is just negative 1 over p squared. The q is gone completely. So when I take the next partial I'm asked to find, with respect to q, this partial, there's no q, it's 0. It would make a big difference if we didn't have to do p twice. We'd still have a q. And as a reminder, let's take the partial of this with respect to q, just so you have a review of your exponential derivative. Go back up in here and say, suppose I want the partial of f with respect to q to begin with. Partial of f with respect to q. My logarithm rule is the same, 1 over pq times the derivative of the inside with respect to q this time. So p is a multiplier, it stays there, derivative of q is 1. Minus, if my derivative is with respect to q, 4p would be a constant, and the derivative of the exponential, I write the exponential the same, multiply by derivative of the exponent, derivative of q squared is 2q. So let's keep going with this. We've done f with respect to q. Let's do p and then p again to see what we get compared to when we did p twice first and then q. If I want to, let me simplify this one a little bit first. Cancel the p's. I have 1 over q minus 8 p, and I could keep the q in front, e to the q squared. And we'll take the derivative with respect to p. With respect to p now, this previous one, the first term, 1 over q, is 0. But I do have another p. 8 is a constant multiplier. This derivative of p is 1, and the rest of the terms with the q's are constants, and they just stay there. Equals negative 8qe to the q squared. Only has a q in it now, and my next partial is supposed to be with respect to p, goes to 0. So it does turn out, for the functions we use, because of the way they're continuous, if you have the same number of letters, you will end up with the same answer, no matter how you do it. It's kind of a way you can check your work.